We are happy to have here today Mercè Guerrero Román. She's doing her PhD at Universidad Complutense de Madrid under the supervision of Diego Rubiera Garcia. So please, Mercè, the stage is yours.
Okay. Thank you very much, Luis, for introducing me and also to inviting me to give this talk. I basically work in, let's say, modified gravity. In particular, today I would like to talk about Born-Infeld gravity. And I also would like to explain you the basic observables that we have in astrophysics about the early evolution of low-mass stars. What do I want to mean with that? It's that we have a baby star that is contracting, and we want to study the main characteristics, let's say, about this construction of the low-mass star from its contraction until it gets to the main sequence and starts burning hydrogen in the core. So once everything is set, I would like to briefly mention how this talk is going to be organized. First of all, I would like to explain you the motivations of why going beyond general relativity, but also why it's interesting to study these astrophysical objects. After that, I also want to briefly explain the Born-Infeld gravity theory. And after that, the basic equations and the model that we are going to use to model these low-mass stars. After that, I will briefly mention the results that we had in this case, which are the Hayashi tracks, the minimum main sequence mass, and the maximum fully convective mass, which these ones are the observables that we are going to discuss today and may help us to constrain our theory. And finally, I would briefly give you conclusions of this talk and the work. By the way, I didn't say that, but this work is about to be finished. I think that by the next month, it's going to be published in arXiv. And it's a collaboration between Aneta and my supervisor, Diego Rubiera. So the first motivation that came to when talking about this talk is why to go beyond general relativity. And the thing is that general relativity is very successful, has passed many tests, and it's very successful. But the thing is that usually when we go to the strong field limit, for example, in black holes, we find the singularities. And there we lose somehow the prediction of the theory. We don't know what happens to particles. So briefly, what I want to say is that it has some shortcomings. And these extensions of general relativity, of modified theories of gravity, basically they try to solve these problems or to do not have these singularities, for example. And therefore, since the strong field limit is somehow changed, when one thinks on constraining or to test these modified gravities, we think on the strong field limit observations, which are gravitational waves or shadows. But actually, gravity plays an important role in less massive objects, and those are, for example, stars. And for example, they could also explain the cooling times of different objects, for example, brown dwarfs or white dwarfs. And this can be done simply by considering different types of theories of gravity. But in this talk, what I would like to focus on is on the early evolution of these low-mass stars. So what happens since this star is contracting and follows what it's called the Hayashi track that we're going to see afterwards, until it gets to the main sequence, and for example, which is the minimum mass that can have this star. And all of this is embedded in this Eddington-inspired Born-Infeld gravity. So one way to extend general relativity is within this metric affine gravity theories, which basically the idea is that the connection is not anymore the Levi-Civita of the metric. So what this means is that we keep or we restore the independence between the metric and the affine connection. Inside these theories of gravities, we have the group of Ricci-based gravities, where this Born-Infeld gravity is inside. And basically, it's constructed by scalars that are built from the independent metric and the Ricci tensor of this independent connection. And the example here that it's written in this action is the action of the Eddington by Born-Infeld gravity, where this kappa is the gravitational constant. Epsilon is this model parameter that when it's equal to 0, we basically recover general relativity somehow. R mu nu is the Ricci tensor of this independent connection, G mu nu, the independent metric. Lambda, it's when it's equal to 1, it basically says that we have asymptotically flat solutions. So for the rest of this work, we are going to assume that this lambda is equal to 1. And finally, we have a matter sector where the matter fields are only coupled to this independent metric. After that, we can compute the field equations and we can write them in an Einstein-like form, where in this side, we have the Ricci tensor of this independent connection. And basically, this Q is what is called the auxiliary metric, which is compatible with this independent connection. I hope that everything is getting clear. Okay, you understand it? And basically, this is something that we define just for convenience to make it more easier. And it's related with this G mu nu, which was the independent metric, by this multiplying this deformation matrix. That on shell can be just written by this algebraic relation that only depends on the stress energy tensor. And if we compare this field equation with the one of the general relativity, we see that the dynamics of the matter sector is changed. Okay, so we are going to work with non-relativistic stars. This means that these field equations that we have before, this one, we have to take the non-relativistic limit. And once we do that, we get the Poisson equation, where basically we have this potential here. And what we can see is that here there's this epsilon parameter, which when it's equal to 0, we recover general relativity, which are these two terms here. So basically, this third term is the correction of considering this Born-Infeld gravity, and depends on the derivative, or the second derivative of the density. Remember that also this kappa is the gravitational constant in suitable units. Another equation that we are going to use is the definition of the mass function written here. And with these two equations, also the hydrostatic equations that basically relates us the derivative of the potential with the derivative of the pressure and the equation of states, we can model or we can model the internal and external structure of the low mass stars. And in particular, for the equation of state, we are going to use the polytropic equation. Why? Because, for example, when we think on an ideal gas, it's also a polytropic equation. A fluid or electron degenerate matter, it's also well described with polytropic equations. And basically, the star is somehow a mixture of these two type of matters, let's say. So the stars can be well described with this polytropic equation of state, where this K will keep the information on if it's an ideal gas, ionized gas, or whatever it is, and it's the polytropic index that for these low mass stars it's 3/2. Okay. If we define the dimensionless variables, perhaps it's better to say if we rescale the quantities of rho by, for example, defining the central density, we have this theta, which somehow it's, sorry, I had to write this equation. But basically what we define is that rho is equal to this central density multiplied by this theta. So from this equation, we also have that the pressure is somehow a function also of the central pressure and this theta here. So somehow now this theta gives the information of the density, and this chi here is the redefinition of the radius, okay? And with this change and using the Poisson equation and this hydrostatic equation that I told you before, which was the relation between the derivative of the potential and the derivative of the pressure, we have this Lane-Emden equation. That this is going to be very useful to define, for example, the mass, the density, the radius, and the temperature of the star. So there's the solution of this equation. It's very important to define these characteristics of the star. And what I would like to point out here is that this alpha is the one that encapsulates this epsilon parameter. That if you remember from the action, this is the parameter that when it's equal to 0, we recover general relativity. And this one is basically which tells us the deviation between our theory and general relativity. So these were the main important equations that we are going to use. And now I would like to remember you what is the Hertzsprung-Russell diagram. So basically it's a diagram or a plot, let's say, of the luminosity or the logarithm of the luminosity in terms of the surface temperature. And once we know, for example, the mass, the age, the temperature, and the luminosity of an object, we can place it on this diagram. And the interesting thing is that only stars that have exactly the same characteristics will be at the same point of the HR diagram. So it tells us the information of the evolution of the stars. So as we can see here, there's a diagonal where, well, or what is called a main sequence, and the stars that are inside there, they are burning hydrogen in a stable way. And here, for example, it's the sun. Here we have the region of supergiants, which are stars that have been running out of hydrogen and start burning higher metallicity elements, for example, helium or carbon or any other stuff. Finally, below here we have the white dwarfs. But as you can see here, we are only discussing objects that are already stars. But I wanted to explain you the early evolution, so what happens before stars before going to this main sequence. And that's basically what is depicted here, which is the same Hertzsprung-Russell diagram, now with the early evolution. Okay, so here we see this red line, almost vertical line here or curve. And this is the Hayashi track. So it's somehow a relation between the temperature and the luminosity. And basically what happens here is that the star is contracting. How do we know that? Because the temperature doesn't almost change. So this means that the surface temperature is almost constant. but the luminosity is changing. So if you remember the Stefan-Boltzmann law, what this means is that if the temperature keeps almost constant, but the luminosity is getting smaller, this means that the surface of the star is decreasing. So the star is is contracting. Also, a nice characteristic of the stars when they are here is that they are fully convective. Okay. Also, an important thing that we are going to use to constrain our theories is that there exists a Hayashi forbidden zone. This means that any star can be inside this zone here. So as we will see, when we have these extensions of general relativity, this curve can be moved, okay? And it could be that at some parameter, this Hayashi track will fall inside the Hayashi forbidden zone and will lead us to a constraint. The last thing that I want to comment about this plot is that the Hayashi the Hayashi track can be stopped with 3 different ways. The first one, it's what we can see here, that it has a minimum. When the star reaches this minimum, this means that the star starts getting a radiative core. So the heat is not transported anymore convectively, but radiatively. And this will make us our star model far more complex, because now we will have to split the star into regions, radiative one and also convective one. So that's something that right now we didn't want to enter in, because it makes our study a lot more complicated. But if you want to know more, when this minimum happens, then the stars follow an almost horizontal line, which is called Henny-Hay track. And basically what says it's that the central is getting radiative, as I told you before. I think that everything is said. In this work, we are going to use this 0.5 solar masses. This M dot here means that it's in terms of the solar masses. So we are going to somehow model a toy model of this case here. And we're going to see how this Eddington inspired Born-Infeld gravity affects this track here. But in order to do so, we basically have to assume something. And the first thing that we assume, and it's okay because, as I told you, the Hayashi track is a star which is convective. So we are going to consider that our star is fully convective and made by a totally ionized monatomic gas of temperature T and molecular weight mu. We will also treat the material to be an ideal gas, and that the surface radiates as a black body. So what does it mean? That this line, we are basically using the Stefan-Boltzmann law that I told you before. We are also using the Lennard equations, and by using the polytropic equations and the ideal gas law, we can have a relation between the luminosity and the temperature. And that's our result. I want to explain you that, first of all, this is a toy model. So if you see here, the temperatures are rather cold. It's 2000 or something. And as we can see here, it's almost 4000. So our analysis is very simple, but what we wanted to show you here is that when we consider different alphas, remember that these alphas were the ones appearing in the Lane-Emden equation. And if you remember, it is the one that gives this epsilon that we have seen at the beginning, which is the Born-Infeld parameter. So when epsilon was 0, alpha equal to 0, we have general relativity. But for example, when we have alpha equal to 0.1, we see that it's shifted. And when alpha is equal to minus 0.1, it's also shifted. So this means that with this alpha, positive alpha, if you remember, it's getting closer to the Hayashi forbidden zone. And this means that positive alpha can be constrained with this type of models. But again, we need to use a more realistic model. The next step, okay, I didn't told you, but okay, there were three different ways of stop the Hayashi drug. The first one is when it develops a radiative core. The second one is that it reaches the main sequence mass. This means that the star's burning hydrogen in an unstable way. And this means that the star is not contracting anymore because the energy that is ignited inside the core of the star is somehow avoiding the collapse of the star. So that's another way to stop the Hayashi drug. And finally, it's the pressure of electron degeneracy. So this means that the star is contracting, but the temperature in the center is not high enough to ignite this hydrogen or start the proton-proton chain. So what would happen is basically that this pressure would stop the contraction of the star. And since they will not start burning hydrogen inside, they will become at some point a brown dwarfs. So once this is said, here basically we are focused on the extreme case. So which is the minimum mass that can have this star to start in this hydrogen burning. So it's the minimum mass that leads to, so that, wait, this is complicated. So the energy that it's lost on the photosphere because of this Stefan Boltzmann law, since it's radiating, it's somehow compensated with the energy that it's generated by this hydrogen burning. So what we do here is basically to equal the luminosity of the hydrogen burning and the luminosity of the photosphere. And by doing so, we find the minimum mass that a star can have to stop burning hydrogen and stop collapsing. So this MMSM is the minimum main sequence mass. This MO dot is the sun mass. Alpha again is this Lim-Emden equation parameter, which is related with epsilon of the Born-Infeld parameter. And what we can see here is that this minimum main sequence mass changes with alpha. By the way, don't look this BAM here, it's just numerical error. So what we see is that, as alpha gets larger, the minimum main sequence mass is also increasing. And right now, this value of the minimum main sequence mass is around 0.093. So this means that this alpha parameter can be at least up to 0.1. So further that, it's not possible because it will not be in agreement with this main sequence mass result. So we have an upper bound here. What I wanted to tell you too is that if you remember, we use the Lim-Emden equations to define the mass. So we have to solve this equation. And when we have alpha negative, what we have seen is that below minus 0.003, this equation is singular. So we couldn't solve it numerically, and that's why it's not depicted here. The thing also is that we have used a very simple model, and what I didn't tell you before is that this alpha not only depends on this epsilon parameter, but also depends on the central density, because of the structure of this Palatini or this type of theories that we are using, that since modify this matter sector somehow affects also in this Lane-Anden equation. So we have to do a guess of the central density. And the thing is that we cannot say that we cannot go below minus 0.003 of the value of alpha, because perhaps the density is smaller, or the central density is smaller, so perhaps this value can be even less. Or if the pressure is bigger in the center, this means that this alpha can be even less negative. So I hope that you understand it. So this is the main result also that we have found here. And also let me remind you again that we have found here an upper bound of alpha, which is that it cannot be bigger than 0.1. Okay, let's come back again to this HR diagram. As I told you before, the Hayashi tracks can end up on this minimum. And here it's where we, or where the stars develops a radiative core. So what we are going to do here is, okay, which is the maximal mass that can have a star to reach the main sequence, so start burning hydrogen, but still being fully convective. So to do so, basically, we have to find where is this minimum and place it just in the main sequence mass. How is it done? So for that, we need this Verschiff criterion. What it basically says is that the gradient, or the temperature gradient, when it's the heat is transported radiatively, has to be smaller than the adiabatic one. When this happens, this means that our heat transport is radiative. So if we want that this minimum it's at the main sequence mass, basically, this minimum says that this inequality has to be, in fact, an equality. So this will be the extreme case, where the stars is still fully convective, but a little bit more temperature, let's say, it will start becoming radiative in the core. So we assume that these two quantities are exactly the same. And using, again, the Stefan Boltzmann law, we can find a relation between the mass and the alpha parameter. Okay, the thing is that here, the photosphere plays an important role too. And the photosphere, it's defined at the radius in which the optical depth is 2/3. What does it mean here? So at some point, we have to model the photosphere of the star. And for that, we need to know the opacity of the star. And the opacity basically tells us how the light is absorbed there. And here we have used two different opacities. This NBF is the mass coming from an opacity called bound free. And what it basically is telling us is how is modeled this absorption when the light is interacting with an electron which is bound with the ion, or the ionizing this electron bounded. Whereas this MFF is the opacity when a light is interacting or is scattering with an iron. So as we can see here, this opacity really plays an important role. I would say that it's even more, the effects, it's far more noticeable than the effects of the alpha parameter, which, remember, it's this epsilon parameter of the Born-Infeld gravity. Because, for example, here in this first case, which is the bound-free opacity, it almost doesn't change, even though, as before, the mass of the maximum fully convective mass is increasing. And here we also see the same, but the gap between these two opacities, it's almost the double. So what we can say from here is that, okay, now we know more or less how gravity affects the internal structure of these low mass stars. But the thing is that from the astrophysical point of view, we really don't know which are the correct opacities. I would also like to point out that the maximum fully convective mass that has been detected up to now is 0.24. So none of these opacities really reach that. And from this fact, we cannot say anything about lambda, about alpha. So we cannot find an upper bound as before. So up to here, it's all the main important results. What we have seen is that usually modified gravity theories, they change the Poisson equation. And the Poisson equation plays an important role in the structure of the low mass stars. Well, not only in the low mass stars, but to all the stars. And since it is modified, and it's an important ingredient, this will lead to different structure of the star. And as we can see, as we have seen here before, the Hayashi track is shifted due to this Born-Infeld gravity. And what we have seen is that, for example, when we have positive values of alpha, these Hayashi tracks are shifted to this Hayashi forbidden zone that may help us to constrain some other parameter. Also, we have seen, well, I have told you that the Schwarzschild criteria is modified, well, due to this Poisson equation that it's also modified. And this is the reason why we have a different maximum fully convective mass, because this Schwarzschild criteria is also changed. And the thing is that this Schwarzschild criteria, it's very important when considering if a region is transporting the heat radiatively or convectively. And astrophysics, we usually use general relativity to model this type of stars, which are more complex and, for example, have this radiative core, but the outer shell is still convective. So with this modification, basically these regions may be shifted, and these limits are not anymore the ones of general relativity. So we have to take it more into account when we model stars. And one application of this Schwarzschild criteria is basically the maximum mass of the fully convective star that is changed with a theorem. And we have seen also the same with the minimum main sequence mass, which was this minimum mass that we need, or the stars needs to start burning hydrogen in the core. From this result here, we have achieved our result, or our main purpose, which was to constrain our theory using this type of early evolution, which, if you remember, is that alpha has to be smaller, or approximately 0.1. And finally, we would like to study the cooling time of round dwarfs in this Born-Infeld gravity theory. And here we would like to use more realistic models, because here we have tried to be analytically the whole time almost. And when we did that, basically our model was so simple that, for example, for the Hayashi track and the maximum fully convective mass, we didn't have any results because they were too simple. So we have to use numerical methods just to have more realistic models, and therefore be more accurate on constraining this theory. So that's all. Thank you for your attention. And now if you have questions, please let me know.
Okay, Mercè, first of all, I would like to thank you for this very nice presentation, and I would like everybody to turn their microphones for a round of applause in retribution for that.